All right, talking about work today. So, in order to discuss work, I wanted to do a little bit of review first, stuff we talked about kind of earlier in the energy unit. So, kind of our review statement here. Energy is conserved in a closed system. So, whenever we talked about conservation of energy in the when we were talking earlier in the energy unit, we said that energy is conserved as long as we're in a closed system. What is a closed system? Closed system means that there are no outside unbalanced forces. All right? So then that means that an open system is, yes, you do have outside unbalanced forces. So for the first part of the energy unit, we lived in closed system land, and now we are moving into open system land, talking about how forces can affect the amount of energy in a system. So when the amount of energy in a system changes, something called work has been done. All right, this is the concept we're going to be focusing in on today. What is work? Well, your textbook definition is that work is when a force causes the displacement of an object. Another way I usually think of work is it's just a change in energy in a system. So, looking back at that first sentence, if the amount of energy in the system has changed, work has been done. Therefore, a change in energy is work. So looking at this, we kind of have two main ingredients for work. We have force, and we have displacement. So those are two key factors that we need in order for work to occur. All right. So let's use that, see if we can build up an equation here. Now, we took data on these things in our work lab. In an ideal world, maybe you didn't see this exactly, but in an ideal world, you would see that as you increase the distance or displacement of the object under an outside force, you would see that the change in energy should increase approximately linearly. You would see the same thing with the amount of force. As you increase the amount of force acting on the object, the change in energy or the work done on the system increased. All right, so helpful, important information there. We're going to take that and use that to help us build a work equation. Now, the work equation kind of has two equivalencies. There's two ways for us to solve for work done on a system. The first one comes to us from the definition we used back a couple pages ago. Work is just a change in energy. So if we find how much energy has changed, we found the amount of work done, right? So we can just take the total final amount of energy in the system and subtract the total initial amount of energy in the system, and that is the amount of work done. On the other hand, we can use the data we collected in the lab, knowing that work is linearly related to distance or displacement. It's also linearly related to the amount of force acting on an object. So we'll say this: work is equal to force times distance. That's it. Pretty simple equation there. What we can do is we can use either of these two methods to figure out how much work has been done on the system. Usually that comes down to what information are we given in the problem. That helps us determine which side of this equation to use. Now, very important to note, when using that second equation there, when calculating work, we only care about the force or part of the force which acts parallel to the distance traveled. Okay, so we're only looking for the parallel force to the distance. Let me show you an example of why that matters. So imagine you have a forklift. I'm going to draw a very bad forklift here, like this. All right, and we have a crate sitting on that forklift, like this. Perfect. So that forklift, we're going to say it is moving forward at a constant velocity. And, well, in order to actually hold that box up, that crate up, it needs to apply a force upward. Okay? So there's this constant positive velocity, which means that we have a positive displacement, right? There, that's our displacement. So we have force, we have displacement. But is the energy in this system changing? No, right? We're not moving up or down. The crate is just being held there. So the gravitational potential is remaining the same. The velocity is not changing, so that means our kinetic energy is remaining the same. So in this case, we have those two main ingredients, displacement and force, but work is not being done on the system. And that's because the force is perpendicular to the displacement here. We're not doing any work. In order for work to occur, we would need to take that force and point it parallel to the displacement. Okay? Very important there. I'm going to add on to my equation here these two lines. That just represents parallel. So that is saying in order to calculate work, I need the parallel force to the distance. There you go. All right, next up we got to talk, is work a vector or a scalar? Well, we're going to borrow a little bit from energy because we know that energy is a scalar. It has no direction. So we'll say that work is a scalar as well, because work is just a change in energy. It just basically is an amount of energy. But whereas with energy, we didn't really talk about positive and negative energy, we do have to discuss positive and negative work because they mean different things. Positive work is when energy is added to a system. Negative work is when energy is removed from a system. Positive work, energy added, it's basically just energy is being pumped into the system. Negative work, energy is being pumped out of the system. Now, in order for positive work to occur, we need to have a force that is parallel and pointing in the same direction as the displacement of the object. In order to produce negative work, we need a force that is parallel but pointing in the opposite direction to displacement. Okay? So this is the condition for positive work. This is the condition for negative work. All right. Moving on, I think we got a practice problem here. So I have a car driving down the road. It is moving at 40 meters per second, has a mass of 925 kilograms. I got 3 questions I got to answer. Question A here says how much work must be done to stop the car. So if we want to bring this car to a full stop, how much work is being done? Question B, if the car stops in 10 meters, how much force was applied to it? All right. And then finally, question C, the force is now applied at a 15-degree angle. Will the car stop after a greater, equal, or less amount of distance? So pause the video here, try these on your own, and then we'll talk answers. All right, so question A says how much work must be done to stop the car? Well, work, let me change colors here. Work is just a change in energy, right? So if I can figure out how much final energy and initial energy is in the system, I can find how much work is being done. Well, if my car is coming to a complete stop, that means it's going to have no kinetic energy at the end. And there was no mention of it moving up or down, so no change of gravitational potential. I think we're going to have 0 energy at the very end. Our initial energy will be however much kinetic energy we had at the start. So I am going to swap that out with K for the kinetic energy of the car. So the amount of work done will just be equal to a negative amount of kinetic energy, however much it started with. So it would be negative 1/2 mv squared. We'll plug in our numbers here. So we said the car was 925 kilograms, moving at a speed of 40 meters per second. Plug that in to our calculators. We should get an answer of about 740,000 joules, negative 740,000 joules. Makes sense, right? We're trying to stop the car. We're pumping energy out, so negative work has to occur. Moving on, question B says, if the car stops in 10 meters, how much force was applied? All right, so this time we're going to use the other side of the work equation. We know that 740,000 joules of energy was removed from the system. We are solving for the amount of force, and 10 meters of distance was covered. All right, so we divide both sides by 10. We find that the amount of force applied to stop this car was negative 74,000 newtons. Finally, we have this last question, part C. All right, now we have this force, and it is being applied at a 15-degree angle. Is the distance our car is going to travel greater than, less than, or equal to the previous problem? So here I'm going to be looking at this side of the equation, right? So work equals force times distance. Because here's the deal. Once our force is at an angle like this, well, now the parallel part of the force is just going to be the x component, right? So the total amount of force stays the same, right? That's still the 74,000 newtons that we calculated in the previous problem. But now we have just part of it pointing parallel to the distance traveled. So in order to calculate the amount of distance traveled, or using the amount of work done, we're going to use a smaller amount of force than originally, right? That's gone down. The amount of force has gone down. Well, the amount of work done needs to remain the same because we still have this car moving at 40 meters per second coming to a complete stop. So the amount of work done needs to be the same amount. We still need to remove those 740,000 joules. So if the left-hand side of the equation stays the same and one variable on the right stays or gets smaller, that means that our distance needs to increase. So that's going to be our answer for part C, is that the distance will increase, get larger. Moving on here, we got to have a quick discussion about the difference between these two types of forces. We're going to talk about conservative and non-conservative forces. In order to do that, we're going to look at a couple examples here. So here's my first example. I have two scenarios. One in which I have a crate that I am bringing up some stairs. So the crate goes up a little, over a little, up a little, over a little, so on and so forth, all the way up to the top. And in the other scenario, the crate just goes up a ramp. In both cases, it's the same exact crate, and the height that they end at is the same. Question is the work done by the force of gravity the same or different between these two scenarios? Well, using our equation for work, you know it is force times distance, force times parallel distance. That'll be important here, right? Because force of gravity points straight down. And if both of these crates are exactly the same, they'll have the same amount of force of gravity acting on them. And the distance that they traveled that is parallel to the force of gravity, well, that's going to be h in both cases. So in both cases, the force is the same and the parallel distance is the same. So therefore, we have the same amount of work done in both scenarios. Let's look at a different situation. Now, so this is a bird's eye view of a crate being pushed across a floor. And here we're asking, is the work done by the force of friction the same or different? Here in the blue line on top, the object is kind of moving in a curved path. Red line on bottom, it is moving in a straight line. So we're going to look at our work equation again. Force times parallel distance. Well, in both cases, the same amount of force of friction is going to be applied, right? Force of friction will be the same because it's the same exact crate. What's going to be different though? Well, the distance traveled will be different, right? This one is taking an arcing path. That is traveling more distance. Therefore, more work is being done on the blue path than the red path. So here, there is a different amount of work being done by the force of friction. So this leads us to the difference between these conservative and non-conservative forces. A conservative force, the path taken doesn't affect the amount of work done. A non-conservative force, the path taken does affect the amount of work done on the system. Examples of conservative forces, force of gravity, like we saw in the one example, spring force, normal force. Examples of non-conservative forces would be force of friction, force of tension, force applied, force of air resistance, otherwise known as drag force. So these are just two new distinctions for forces, how we can categorize them in different ways. All right, moving on. We got to talk about power very briefly. It's a pretty easy topic. We won't be talking about it for too long. What is power? Power is the rate at which work is done on a system. We're going to use that definition to come up with an equation. Power is represented by a capital letter P. If it's the rate at which work is done on the system, then we just got to figure out how much work is done and how much time it took for that work to occur. That's it. Power is just a measure of how fast energy is entering or leaving a system. What is it measured in? It's measured in units of watts, or sometimes measured in units of horsepower. Though most of the time in this class we'll be using watts. Horsepower is just a common one you see used in the real world, right? People use it for cars often. Okay. The conversion from horsepower, for each 1 horsepower, there's 746 watts. That's not something you need to memorize. If you need to know that, I'll let you know that conversion. I'll tell it to you. Okay. There is an alternate equation for power that is just a different way to calculate it. And essentially, it's just a rearrangement of the original power equation. What we're going to do is we're going to say, well, work, I know, is just force times the parallel distance divided by time. And then you might see in there, well, distance over time is just velocity, right? So our second kind of alternate power equation is force times parallel velocity. Okay. That is all we need to know for force, or for power. This is a practice problem here for you to try. Go ahead and pause the video here and give it a shot. I will run through the answers. For part A of this practice problem, we have a car driving up a 10-degree hill at a constant speed of 22 meters per second. Question is, how much power must the car produce? Part B, we have a car on a flat road. Same car on a flat road accelerates from 25 meters per second to 30.6 meters per second in 6 seconds. Question is, how much power did the car produce? All right, so in both of these cases, very important to note, the car has a mass of 1,400 kilograms and is experiencing a friction force of 700 newtons. We're trying to figure out how much power is the car producing. So how much power is this force right here enacting on the system? So for the first problem, we have a car at constant velocity. That's important. The car at constant velocity is very important because that means that all the forces acting on the object are balanced and equal. So I'm going to draw a free body diagram for this car. I'm going to say that this is FC, I'll call it, it's like the car force, the force of the car. Here's force of gravity. I'm tilting force of gravity, right, because we're on a ramp, so it's just like those old ramp problems we used to do. So I've tilted my axis to make everything just a bit neater. Force of gravity is on an angle, so I'll split it into 2 parts. We have FGX and FGY. And that is 10 degrees right there. Okay, so I want to solve for the amount of power this car is producing. I'm going to use the second power equation, force times parallel velocity. Because I know the velocity was 22 meters per second. That was given in the problem. The force is what I need to calculate. It's this FC here, the car force. Well, because the object's moving at constant velocity, that means all the forces acting on it are balanced out. So that means that the car force, which is pointing to the right, is going to balance out with the x component of gravity, which is pointing to the left, and force of friction. Okay, well, we can solve for that, right? We know that the x component of gravity we can solve for using mg sine of theta in this case. And we're told that the force of friction is 700, so we don't have to calculate that, which is good. All right, so the mass is 1400, G is 9.8, sine of theta, theta is 10 here, plus 700. So we plug all that into our calculator, come up with an answer. I need to add 700 to that. Our answer is 3,082.45 newtons, right? This is our car force. Okay, cool. Now I just take that force and plug it into my equation up here at the top. So 3,082.45 newtons times the velocity of the car of 22. So we find that the car is producing 67,813.9 watts. That's our answer. All right, so for part B, we're on a flat surface. We are accelerating from an initial velocity of 25 meters per second to a final velocity of 30.6 meters per second in 6 seconds. Okay, so again, I think I'm going to use this equation here. But this time, finding the force from the car is going to be a bit more difficult. I'm going to use Newton's second law, net force equals ma, but I don't know the acceleration of my car. So let's find the acceleration of my car. Acceleration is just a change in velocity over time. So the change in velocity would be final velocity of 30 minus initial velocity of 25 divided by 6. That comes out to an acceleration of 0.93 meters per second. All right, so I'm going to write that down over here real quick. Oh, meters per second squared, I should say. All right, now I'm going to take all this and plug it into Newton's second law and say that we have the positive force from the car minus the negative force of friction equals mass times acceleration. So we have car force minus 700 equals 1400 times 0.93. Plug that into our calculators, we get a force of, let's see here, 2002 is the car force in this scenario. And we'll take that, plug it into our power equation. Here, let me move that over a little bit. Okay. So our power is going to be equal to 2002 times our final velocity of 30.6. Our answer is 61,261.2 watts. And there you go. All right, that covers work and power for us. Hope this was helpful. I'll see you later.